Good day and welcome to this tutorial. In this tutorial, I will show you how to make use of the electrolyzer that is currently inbuilt in the Aspen HiSys software, right? So the Aspen HiSys version 14 is an improved version of the software, and some additions have been made to make your simulations better. And one of those additions is the introduction of the electrolyzer to the model palette, right? So in this video, I would like to show you how to make use of the electrolyzer equipment in the model palette, right? So quickly, we just start by creating a new case, right? So we just create a new case. Yes. So in our new case, we go ahead to add the components. So for this illustration, we are working on the alkaline electrolysis, which is what we actually did in the last electrolysis tutorial we had, right? So the electrolysis has already been introduced in those particular tutorials. So in case you need more information about electrolysis, you could actually check them out. And these were some of the um, uh, journals that we made reference to. So in case you still need more information, you can check this journal, this particular one. Then also, we also have this as well, right? So you can check this one, and then let me see. Also this one too. Also a good journal to give you information about electrolysis and electrolysis modeling in general, right? So going back to what we have, so we are trying to model or illustrate alkaline electrolysis. So we add our components. So for components, we'll be making use of the Aspen properties database because based on the kind of fluid package we'll be using, so we add components. We have water, then we have hydrogen, then oxygen. Yeah. So and we are trying to simulate alkaline electrolysis, which automatically means we need an alkaline. In this case, we'll be making use of potassium hydroxide. We also include that in our component list, and then we can go further with our model. So the next thing is to specify the method. So we click on fluid packages, and then we also work with Aspen properties database, and this has already been explained. So we use Aspen properties database for components. So automatically you also use that for selection of the fluid package as well, right? So for this particular illustration, we'll just make use of the um, electrolyte NRTL. The electrolyte NRTL is suitable for the modeling of electrolysis and electrolytic processes, right? So we make use of the electrolyte NRTL. Okay, so after specifying the um, fluid package or the method, the next thing to do is to go to the electrolyte wizard. So you make use of the electrolyte wizard specifically for this particular process because we have the splitting of the uh, components into the respective ions, right? So we click on that and it brings us this window. So from this window, we are highlighting all, then uh, for hydrogen ion type, you can either choose this H3O plus or H plus. So I'll just go for H plus. Then it says includes reaction of. So in my case, I will select water dissociation and I will deselect salt formation. Then after doing that, I will click on get reactions, right? Get reactions. Yes. So after clicking get reactions, it brings up the reactions that are associated with the process. So you have the H2O splitting to H plus and OH minus, and then KOH splitting to K plus and OH minus. So you click select all and then you click OK, right? Okay. So both of them have been specified. So it is after these specifications that you can now go into the simulation environment. Okay. So in the simulation environment, right? This is your simulation environment um, for version 14, right? And slight changes have been made to this particular version. So you can be seeing things like AI, right? You have AI training, AI model builder, and also you have slight changes in your palette as well. So in your palette, the streams have been updated. You have power streams, right? So you have a power stream now. So you have three streams. You have the material stream, you have the energy stream, and then the power stream. Then also for your equipment, you can see that an electrolyzer has been added to the model palette, right? An electrolyzer. Um, you can see that at the bottom left of my screen, my cursor. That's what we'll be making use of in this particular model. So this model will show you how to actually utilize this particular equipment. It will also give you information about the key parameters you need to specify, right? So yeah, so we can start with okay, we can just get out the electrolyzer, right? Now, this is basically how it works. Electrolyzer is an equipment that requires input and output streams just like other equipment. It also requires a power stream, right? It requires a power stream. Yeah, and basically that's it. And it requires you to make some specifications, right? So, and it's used for the electrolysis of substances. In this case, our example is the electrolysis of water. So we are making use of this particular unit to represent the stack, right? So first things first, we can actually specify the material streams first. Doing that, we just need to type in the name of the stream. Now, before we do that, we have different models for the electrolyzer. You have the simple model and then the rigorous model, which will require more input, right? So for the simple model, you have the single feed stack, you have the dual feed stack, electrolyzer module. So the single feed stack is a scenario where you want to input only a single feed stream, while the dual feed stack is where you want to have two feed streams to the unit, right? So maybe in a case where you want to separate the addition of the um, alkaline and the water into the unit, you might want to use the dual feed stack. But assuming I want to actually model those two components coming in together, then I use the single feed stack. So for example, let's assume I want to make use of the single feed stack, then I would have to, or it would require me to use a mixer, right? I will need to use a mixer to actually start the model. So if I have a mixer here, I can actually use the single feed. So I create two streams for water and the alkaline, and then I can create the equipment outlet. So I'm creating these material streams by just typing the names I want to represent them with. So I can specify composition for each stream. So for water composition, we just make the assumption that we have only water in that stream, and then same goes for the alkaline. We have only potassium hydroxide in that particular stream as well. Then what else? Okay, for water, we can use let's say 70 degrees. So I'm assuming that the water and the alkaline are already in states where they would actually be as required in the electrolyzer, right? So for this, we'll be making use of 7 bar for pressure. So these conditions are conditions, operating conditions for electrolysis, that is alkaline electrolysis generally, right? So I'm making the assumption that these components are already in that state. So I don't need to start specifying all of that or start modeling them to that state. I just want to illustrate how the electrolyzer works. That's the um, basis of this particular tutorial. So as you can see from one of our journals, you can see why I'm using some of these. You can see why I'm using some of these conditions. So we check from here. So you can see some of the operating conditions here in this particular journal, right? You can see some of the operating conditions. Basically, that's why I'm making use of those values. And by the way, um, the recommended amount of alkaline required is within the range of 20 to 40 weight percent, right? 20 to 40 weight percent. That's the amount of alkaline that is required for alkaline electrolysis. So you also have to take note of that. So we are good with the initial specifications. So we can send the mixture into the electrolyzer. So I can adjust this label, just adjust it, and then I can feed this as a single feed to the electrolyzer, right? So to get the error messages for the electrolyzer, all you need to do is just scroll down and you can find it. So this can guide you on what you need to specify. So it says requires a product stream. So product stream is your anode outlet and your cathode outlet, right? So remember, in electrochemistry, your anode is the positive, yes, is the positive electrode, and your cathode is the negative electrode, right? So automatically you have like charges repel, unlike charges attract. So the positive ion will go to the cathode, which is the negative electrode, while the negative ion will go to the cathode, the anode, sorry. Negative ion goes to the anode, the positive ion goes to the cathode, right? So and for electrolysis, what we have is water is breaking down into um, hydrogen and oxygen ions, of which hydrogen is the positive ion and oxygen is the negative ion. So automatically, oxygen ion will go to the um, oxygen ion will be going to the anode, yes, because it's the negative ion, and the positive ion, which is the hydrogen ion, will go to the cathode, which is the negative electrode, right? So basically, that's how that works. Then also, we can now attach, we can attach, let's say, we can attach power stream, right, to this electrolyzer. So we can flip this, yes, change the direction of this, and then we bring in a power stream, right, and we attach it to the electrolyzer. So let's check the error message we are having now. Okay, now it says requires a power stream, right? So we can just attach this to the stream, and it says power or current must be specified. While in this case, you also have energy as well, of which you can also specify your energy stream, right? That will cater for, yeah, the change in temperature, yes. In case there is a change in temperature, the energy stream will cater for that. So I can just specify, let's say I specify Q1 here. No, not at the inlet. Sorry for that miss. So not at the inlet. I wanted to specify. Okay, so I've specified it as Q. That's the energy stream. Let me change it here. Just change the name to Q1. So we are good to go. So yeah, I can rotate that. Just rotate it so it's like this. Yes. So this is good now. Okay, so we now specify more details for this our electrolyzer. So we can specify the power. So one of the parameters you have to specify for your electrolyzer is actually the power, right? You have to make sure you specify power for it. So for this particular model, I will just be making assumptions. So just to show you how to specify those very important parameters, right? So to make your specifications, what you need to do is click on parameters, right? We have connections, and then we have parameters. All of them are under the design tab. You can see them at the top left of my screen, right? Under design, you have connections, parameters, options, user variables, and nodes. So under parameters, you can specify the different parameters that are required for your electrolyzer to solve. So in this case, I just want to use a power of 5,500 kilowatt. So I've been able to specify that. And next, it is asking for the duty or outlet temperature. Now, it is requesting for this information because of the um, energy stream I added. So based on this energy stream, it is requesting for the heat duty, right, of the electrolyzer, right? So I will just specify outlet temperature instead. So you can either specify the duty or you specify outlet temperature. So I will go for specifying outlet temperature, and for that I will assume that temperature was maintained. So we will be having 70 degrees Celsius. So we have 70 degrees Celsius for temperature, right? Then for pressure, I will also assume that pressure was also maintained in the electrolyzer. So I'm assuming there is no pressure drop. Yes. So basically, once I make all these specifications, the electrolyzer gets solved, right? So basically, this is how to model an electrolyzer. Now, let's go into more detail about the specifications. So I have told you about the temperature or the duty specification and also the pressure, which you can also assume that there is a pressure drop and specify maybe less outlet pressure, or you specify the pressure drop depending. So, but okay, let's go back to the parameters. Now, for the parameters, you have different parameters right here. Um, you have your number of stacks, and you have your number of cells per stack. These are parameters you are expected to specify. Default values for them are already indicated, right? Which this won't be the values you would use. So you get your values for number of stack and number of cells per stack based on your research. So usually for alkaline electrolysis, usually between I think 5 to 12 stacks and about 50 to 200 cells per stack, right? So these are things you have to specify. Also, you can adjust your Faraday efficiency to be between I think 85 to 95. Yes, within that range for Faraday efficiency. Then you also have voltage efficiency as well, right? Voltage efficiency, which you can specify. You can specify that by deactivating this HHV as the higher heating value efficiency and activate voltage efficiency instead, right? So any of them you want to specify, you can actually activate that one and specify it. So for example, I can um click on voltage. Okay, okay, based on the current parameters we have, let's check our worksheet. So our worksheet shows us the composition of hydrogen. So you have about 0.836 hydrogen, right? That's what you have for the current specifications we've made, right? Now, if you adjust some of those parameters, you see that the values would actually change, right? So we have 0.836. And if we check performance, we also have more details about the calculated values from HYSYS. So you have um, calculations and results for hydrogen molar production rate, oxygen molar production rate, water molar consumption rate, hydrogen mass production rate, oxygen mass production rate, water mass consumption rate, hydrogen purity. So you have oxygen purity in terms of mole. You have anode vapor fraction, cathode vapor fraction. You have specific molar energy consumption, mass consumption, specific molar water consumption, and a lot of other parameters have been specified here. You have the total current, total voltage. All of these are from the power stream, right? So basically, you can see the different values for these parameters, right? So for mass consumption, we have about 1248 kg per hour. Now, if we change some of those values, you will see that it will actually have an effect on it. So let's say we use 85 here, 85% for Faraday efficiency, 85% for Faraday efficiency. Then we activate voltage efficiency and we reduce voltage efficiency to say 99%. 99%. Now, if we check the performance, we see that the water consumption reduces, right? It reduces to 1055, right? Reduces to 1055 kg per hour. And we also see that hydrogen purity has also reduced, right? Has reduced to 0.6233, 6263, right? 0.6263, right? So these different parameters with of which you specify here, right, have an effect on the amount of hydrogen that is being produced, also the amount of water that is being consumed, right? So these parameters are very important and will determine how effective your electrolyzer will work, right? So that's why you need to actually specify values that will optimize the production of hydrogen from uh, the electrolysis of the water, right? So basically, this is how this works, right? This is how it works, and we can also check the power, right? So this is your power stream, of which if you specify voltage and current, I believe power can also be calculated as well. So we can actually optimize these different parameters using the case study in the software, right? So let's see how these parameters will actually have an effect on the amount of hydrogen produced uh, from the electrolyzer. So we already discussed how to use the case study in a previous video. So in case you need details about it, you can let me know in the comment section and I'll share the link with you, right? So on that case study, I will just click add, and we'll be making use of some of the specified variables. So let's see what we can use. Okay, let's use Faraday efficiency, the voltage efficiency, then the total electric power. Then temperature, for temperature, okay, let's say we use the temperature of water, for example. Let's just say we use temperature of water for illustration. So these are our input variables, which are the independent variables. Then for dependent variable, I just want to focus on how much hydrogen is being produced from the electrolyzer. So I will still be making use of the electrolyzer as the object type. Then we are working with hydrogen. Let's see. So hydrogen production rate in mass basis, that's what we'll be working with, right? So it gives us the value, the current value, right? The current value. So we can work with this, right? So we go to case study setup, and then we specify details. So number of steps, I will just make use of 20 for each of them. So for Faraday efficiency, we just go from 50 to 99. Let's do same for voltage efficiency. Then for electric power, let's say we start from 3000, or let's say we start from 1000 kilowatt to, let's say, 6500. Then for water, let's just do the range. Let's do 60, or let's do 50 to 90 degrees Celsius, right? And the number of steps for each of them are 20 respectively, right? So we just run this, and then we can run the case study. Okay, before we continue, I would prefer to use the other option, right? So this has actually run, but I would prefer to use the other option, which is the sensitivity, right? I would prefer to use the sensitivity. So it reduces the number of states since I'm making use of multiple input variables, right? So I will just change it to um, sensitivity. So I want to have fewer number of states. So instead of having 1600 or the value I had before, I will just have less than 100 states. So it can be easy for us to analyze the results. So I'm making use of the same ranges I inputted before. Then this is 50 to 90. So the recommended temperature is actually 70 to 90 for alkaline electrolysis. So just to specify this, yes. Okay, so we have 80 states. That's for this. And then we can run it and check the results. So we just run and we have successful run. So you go to the results. So these are the tables for reference sake. You can export to Excel and then you have the plots, right? So these are the plots for your case study, right? So you have hydrogen production against Faraday efficiency, voltage efficiency, total electric power, and temperature, right? So from our case study, we can see that as Faraday efficiency increases, you have an increase in hydrogen production, right? You have an increase in hydrogen production. Then you can also check for voltage. So voltage is similar to Faraday. Voltage is similar. Then we also have total electric power. Yes. So as you increase power, you have an increase in the production of hydrogen from the electrolyzer. So from 1000 to 6000. So you can see there is also an increase. Then let's see temperature. Okay. Water temperature did not really have an effect. Yes, water temperature did not really have an effect. So I was looking for a way to get temperature of the mixture, but that is not an input variable, right? That's not an input variable. So I guess we'll be leaving out the temperature for now. But basically, that's how this works, and you can use it to actually optimize your parameters, right? You can actually use it to optimize your parameters. So basically, we were looking at the simple model, right? So I would like to show us how the rigorous model also works. So for the rigorous model, let's assume we select the single feed stack for rigorous. So that will take us out of the OK message. It says missing internal parameters information. So there are some parameters we are supposed to specify that are missing. So whenever you activate the rigorous model, these internals also get activated, right? So you have the internals parameters that you would need to specify before your electrolyzer will solve, right? But this works with the rigorous model, right? So the different parameters are there for you to specify. So they are all here. So you have the geometrical parameters, then you have the electrical parameters, which are under the electrodes, right? Then you also have the membrane. Under membrane, you have the membrane parameters. and then additional parameters, right? So these are the different parameters you have to specify if you are using the rigorous model, right? So the rigorous model basically requires more information, right? Requires more information from you. So going back, we can now specify certain things. So these values that you have here, these values here are just default values which um you can actually change based on your research, right? And based on the kind of output you are looking for, right? So, but to solve this, all we need to do is add values for active area. When you input values for active area, it automatically solves because the other parameters have been specified, like the width of channel, length of channel, thickness, porosity, tortuosity, pore radius, electrode roughness factor, right? So basically all these values are in their default settings, right? So you are expected to specify whatever values you find that are reasonable for each of these parameters. So specifying for area, active area, just an assumption. So if I specify active area for both of them, okay, I want to use 0.01. So I will specify this again. This is just an illustration. So after this, it says pressure is over specified. So that was based on our initial specification in the that is in the simple model. So I will just remove this pressure value. I will remove the pressure value, and then I will go back. Okay, so it has solved. So let's see the parameters. So for pressure drop, we use correlation, and also we use correlation. Also, another very important parameter is this feed split ratio, right? The feed split ratio, right? So it determines the amount of feed that enters or that comes out. Yes, the amount of feed that comes out from the anode and the cathode, right? Is your feed split ratio, which you are also supposed to specify in the simple model, right? So even when you are modeling using the simple model, you are supposed to specify your feed split ratio, right? So basically, for the internals, you basically need more details or more information to actually specify your internals for the rigorous model. Um, Results from the uh, stack. So we have three performance results here. We have three performance results. We have you have all results. You have results from the cell, and then you have results from the stack, right? So you have stack results, you have cell results, you have system results as well, right? So this gives you different information about your model, right? Gives you different informations that are necessary from your electrolyzer, right? So with this, we have come to the end of this particular tutorial. So if you have further questions about how to make use of this electrolyzer, you can let me know in the comment section. Like this video, share with your friends, and subscribe to this channel if you have not done so yet. Thank you for joining me in this particular tutorial. Do have a good day.